Hello class, today I'd like to talk a little bit about gravitational potential energy. In particular, we know that gravitational potential energy around the surface of the Earth is mgh, and around the surface of um, any planet would be mgh, where we have to just replace the g with the strength of gravitational pull for that particular planet. What we want to talk about today is how to correct this formula for calculating the gravitational potential energy when we're a very big distance away from a planet. When we wanted to talk about the force of gravity on an object, we had to use Newton's law of universal gravitation, G m1 m2 divided by r squared. What is the gravitational potential energy formula when we're very far away from something? Now, to motivate it, I'd like to talk a little bit about Voyager 2 spacecraft, which was launched in 1977 and is now one of the furthest human-made objects away from the Earth. It's actually just last fall was declared to be in interstellar space, which is the area in space that is said to be far enough away from the sun that it is no longer influenced as strongly from the sun as from any other star in the sky. And this is the first object that humans have ever made that has entered interstellar space. Now, it's going to take 400,000 years to get to the next star, which is another story, but it is a pretty significant accomplishment. So we wanted to make certain that when Voyager 2 started on its path, it had enough energy so that it could leave the solar system. We all know that if we take something and we throw it up from the surface of the Earth, it's going to return to the surface of the Earth. But if we can throw it fast enough, maybe it'll be going quick enough that it will never return to Earth. It can even get away from the sun without returning to the sun and falling back towards the sun. It's moving fast enough that it can escape the pull of the sun and travel forever and ever into interstellar space. And that's exactly what scientists wanted to do with Voyager 1 and Voyager 2. Now, they had to ask themselves, well, how do we make certain that we launch this spacecraft so it's going fast enough that it will in fact leave the solar system and travel into interstellar space and not return to the solar system? So you would begin by looking at the force exerted by the sun on Voyager 2, and we would have a graph like this. When it was launched, it was about 5 times 10 to the 11th meters away from the sun, which it wound up being a force of about -4 newtons. A -0.4 newtons were exerted on Voyager 2. And then notice as we got further and further away from the sun, the force exerted on it got smaller until in fact we were out by Pluto, which is about this distance here, and it was only about half a newton, or I'm sorry, 5/100ths of a newton exerted on it. Notice that they're negative forces because the direction that's typically chosen when we're talking about forces exerted in space is that an attractive force is a negative force and a repulsive force is a positive force. So in this case, it came out negative. Now, if we wanted to calculate the gravitational potential energy of the Voyager 2 at different points, at different distances from the sun, we would find the area in between this graph and our horizontal line that would tell us how much work is done by the sun on the Voyager spacecraft. And then if we know how much work is done on the sun, if we change our system, that's going to be equivalent to the amount of gravitational energy that the system of the sun and the Voyager 2 has. So if you do all this, now you wind up needing to use calculus in order to figure out what the gravitational potential energy formula is, but you get a formula of this form: G, gravitational constant, we all know what that is, times the mass of the two objects in your system divided by the radius. This is a little different than our formula for the force exerted from one object on another, because it's not the radius squared, it's just the radius in our denominator here. And this is in fact what you would use to find the gravitational energy. So in the case of the Voyager spacecraft, when it left the Earth, it had a certain amount of negative gravitational potential energy. Negative because our formula tells us that's the case, and also because the point where the spacecraft has no gravitational potential energy is some position very, very far away from the sun. That's where we set the 0 point for gravitational potential energy to be. So now that we're closer to the sun, it's become negative. And the Voyager spacecraft started with some kinetic energy. And in order to make certain that it could escape the influence of the sun, we had to make certain it had more kinetic energy than potential energy, so that when you're way out at a point where there's practically no potential energy, you still have enough kinetic energy that you're going to keep moving. All right, so if we calculate it, the Voyager spacecraft started with negative 6.4 times 10 to the 11th joules of negative joules of gravitational potential energy. In order to escape, we had to make certain it had at least this much kinetic energy, so that afterwards it would be able to continue moving even when it had no potential energy. So in order for this to be the case, it had to be moving at least 42 kilometers per second to escape the sun's influence. So that's how quickly the spacecraft had to be going. Now, that seems quickly. Spacecraft that are in orbit around the Earth are moving probably at about 10 to 14 kilometers per second, so it's possible for this to actually happen. All right, and here's the answer to our question. How fast do you have to launch a spacecraft so it escapes the influence of the sun and doesn't return? Well, 42 kilometers per second was about what it was. This is what the escape velocity is. It's the required speed an object needs in order to be launched so it will not return to the originating body. So if you wanted to throw a stone, you would need to throw it faster than the escape velocity from the Earth so that it doesn't return to Earth. It just keeps flying into outer space and goes on forever. If you had a stone and you were standing on the moon, you would have to throw it faster than the escape velocity for the moon in order to make certain that it never came back to the surface of the moon. It just kept going and went on forever. Okay, so what we learned about today was that we can replace our traditional formula for gravitational potential energy, MGH, with the more accurate one that takes into account the fact that the force between two objects changes as the distance between them changes. And so this is our much more accurate gravitational potential energy formula that can be used on scales of a solar system. And then we also briefly defined escape velocity as being how the velocity that's needed for an object to escape the gravitational interaction with another object. Okay, thank you very much.